Well, welcome back, students. We're now going to begin the chapter on molecules and compounds. If we only had the elements that appeared on the periodic table, then the amount of chemistry that could be done might be limited. But we have a wide variety of molecules made by joining atoms of the elements together to form compounds. And in this chapter, we'll begin talking about how atoms bond together to form compounds. There are two basic ways, I'm sure you know this, ionic bonds and covalent bonds. But first, let's talk about how we represent chemical formulas. The term chemical formula is a very general term. To be more specific, we could refer to either an empirical formula, molecular formula, or a structural formula. So again, the chemical formula is just the broadest term. An empirical formula is the lowest ratio of atoms in a molecule, and we'll see what that means in a second. A molecular formula gives the number of each type of atom in a molecule, and a structural formula attempts to show how they're connected in space or to give some three-dimensional perspective. An example, a molecule called hydrazine. The empirical formula for hydrazine would be NH2. That is, for every one nitrogen, there's two hydrogens. The actual molecular formula is N2H4. That is, in this molecule, there are two nitrogens and four hydrogens. Now, when we represent a molecular formula, we try to write it out in a way that makes some sense. Typically, we do not list the atomic components of a molecule in alphabetical order. For example, if we were to write out H12N3PO4, alphabetical order with the number of each in a molecule, that would actually not make much sense to a chemist. They would be scratching their heads trying to figure out what this is. But instead, we try to group the atoms together in a way that makes more sense in terms of the structure of the molecule. For example, if for the same H12N3PO4, if we were to write it as NH4, three NH4s, and then PO4, then it's pretty clear to any chemist, and maybe even to you, that this is ammonium phosphate. You see the difference? Now, the structural formula is an attempted representation of the molecule in three dimensions to show what it actually looks like. For hydrazine, we might write it in this way. Notice those dots turned out to be important. They are what we call non-bonded pairs, and we'll get to those. The dashes are always some type of bond that holds the atoms together. We might also represent hydrazine in the following way, where we have wedges and dashes to try to indicate some three-dimensional structure. That is, the wedges are coming out of the plane of the board or the screen, and the dashes are going back. Or we might represent it in this manner, which is a ball and stick representation, or even in a space-filling representation shown here. So these latter four are all structural formulas. Of course, some are easier for you to draw than others. To give you another example, consider the molecule known as benzene. Its empirical formula is CH. That is, for every one carbon, there's one hydrogen. But CH doesn't make a lot of sense because there can be other things that have that empirical formula. Instead, it's more useful to give its molecular formula, which is C6H6. That is, there are 6 carbons and 6 hydrogens in this molecule called benzene. Even more useful is to give the structural formula, for which I show 3 different representations. The representation to the left draws out the carbons as carbons and the hydrogens as hydrogens and shows the bonds that link them together. Notice the single bonds and the double bonds linking the carbons together. Or we can show a ball and stick representation shown in the middle, or a space-filling model, which happens to be rotating in this case. Now, before going further into molecules and talking about those bonds, those things that hold the atoms together, let's talk about how we name molecules. And let's first talk about how we name ionic compounds, and then we'll talk about how we name molecular compounds. For ionic compounds, for it to be a compound, it must be neutral. That means the charges must all balance add to 0. When we name an ionic compound, we name the cation first, and the cation is often a metal. We name it first. Now, it might be useful for you to have some ionic compound in mind, such as sodium chloride. Notice sodium chloride. Sodium is the metal. We named it first. Then we name the anion second, and we changed the ending of the anion. We didn't change the ending of the metal. We said sodium, the same as we call it as a metal. But we changed the name of the anion from chlorine to chloride, sodium chloride. And we represent the smallest whole number of these anions and cations in the molecule. To give you an example, for the ionic compound made of the +3 cation of aluminum and the -2 anion of oxygen, what we call oxide, to form a neutral ionic compound, we would need, we would need 2 of the +3 aluminums and 3 of the O-2 oxides. That's so that we would have the same number of positive charges and negative charges. There would be a total of 6 positive charges and 6 negative charges. This then forms Al2O3. Okay? Now, what do we call this molecule? We call it aluminum oxide. Aluminum, the name of the metal, oxide for the anion, and notice that we've changed oxygen to oxide. Notice also in this example that we can rationalize or figure out how many of the cations and how many of the anions, if we know or if we're told the charge on the cation and the anion, and many of these you will know, you'll see shortly, you'll know because I'll give you some rules. And then using rule number 1, that for a molecule the charge has to be balanced. It has to be 0 net charge. Okay, let's continue. As we said, the cation's name is not changed. So if for something like sodium chloride, the sodium has the same name as if it were for the element. Okay, the anion we changed from chlorine to chloride. And now let's look at this next rule. For monoatomic anions, an anion that comes from a single atom. For monoatomic anions, they end in IDE. Nitrogen becomes nitride, phosphorus becomes phosphide, oxygen, oxide, sulfur, sulfide, chlorine, chloride, fluorine, fluoride, etc. And some other simple anions also end in IDE. Hydroxide is OH -1. It's not a monoatomic anion, but we still give it an IDE, an ide ending. CN- is cyanide. O2 -2 is peroxide. Now I might point out that the O2 -2 is a tricky one that you have to always keep your eye peeled for. Oxyanions. We'll have the whole next slide. We'll talk about oxyanions. They are a little bit more complicated, and we just have to learn the oxyanions. They will end at 8, ite, us, and there are some additional ones, like besides the ones I show in the next slide, such as dichromate, Cr2O7 -2. See, it can get a little complicated. Permanganate, MnO4 -1. Cyanate, OCN -1. Cyanate. Distinguish cyanide as Cn -1. Cyanate, OCN -1. Thiocyanate, SCN -1. You'll learn a little trick that when you say thio something, it means you substituted a sulfur for an oxygen. So thiocyanate, SCN -1. And acetate, CH3CO2 -1. Now this will look complicated, but a little later on you'll find that it's not so difficult at all for acetate. Transition metals. When we have a transition metal as a cation, we really don't know what its charge is going to be, except in maybe a few cases where we know that silver is always going to be +1, for example. But in many of the other cases, it's uncertain as to whether or not the charge will be +2, +3, +4, etc. So the rule we use is that we tell each other what the charge is by using a Roman numeral. For example, if I say, write out FeO and I try to give it a name in English, it is iron, Roman numeral 2, oxide. You got that? Iron 2 oxide. And if I write that out in a text message, for example, iron, parentheses, Roman number 2 oxide, then someone on the other end would write out FeO. knowing that the iron is a +2 cation, and oxide, because they know that oxide is -2 because they followed the rule above, and that the molecule has to have no net charge. Similarly, what if I'm thinking about another oxide of iron, this one being Fe2O3? Let's think about that. Fe2O3. Oxygen is going to be, as oxide, is going to be -2. And I got 3 of them, so I got 6 negative charges. And if it's Fe2O3, that means the iron has to be a +3 cation. Right. So, in English, I would write this out as iron, Roman numeral 3, oxide. This is the way I would write it out in English. And that would be Fe2O3. Now let's go back to the number 5, the oxyanions. You might be wondering, what is an oxyanion anyway? We'll have a next slide in which we'll talk about oxyanions. But in a larger sense, oxyanions are also what we could call polyatomic anions. And there are polyatomic cations. And what we mean by this, again, the next slide is coming, but we mean things like CO3 - 2. Species that hang together, they diffuse together, the carbon and 3 oxygens in CO3 - 2, something we will call carbonate. They are a single entity. For a polyatomic cation, an example would be something like NH4+1. The nitrogen and the 4 hydrogens are bonded together to form a +1 polyatomic cation. We will call that ammonium. It's about the only one you really need to worry about in general chemistry is ammonium. There's 1 or 2 that you might see in a book, but for the most part, when we talk about a polyatomic cation, we're going to talk about ammonium. And notice that it's different. I said ammonium, like sodium, IUM, different than ammonia, which we'll get to later on. Now, also, before going to this next important slide, let's point out that when we have polyatomic species, whether they're anions or cations, sometimes we have to use additional parentheses to make sure people don't get confused. So look at the example that I've just shown you. If you have iron 2 hydroxide, if I were to write out iron 2 hydroxide as a chemical formula without the parentheses, it would look confusing because I might write FeOH3, and one might think that there's 3 hydrogens and only a single oxygen. So we have to use parentheses so that whoever we're showing this to knows that we have 3 hydroxides. So when we use polyatomics, we usually also have to use parentheses to make sure people are not confused. The rule always is we try not to confuse people. We try to make it clear to whoever we're trying to communicate with exactly what molecule we're talking about. Now, let's go on to the oxyanions. And the rule here, now this is an important slide. You may even want to print it and look at it carefully for some time. What I tell people is to know the eights. The eights is the second row. It's the most complete row, the second row in this table. If you know the eights, then learn how to go up and down in the table. And notice at the top, I start with carbon, nitrogen, phosphorus, sulfur, chlorine. That is, these are the elements in the periodic table, and I'm showing the oxyanions, the polyatomic anions, the oxyanions that can be formed from each of these elements by adding 1 or more oxygens. So, for carbon, the oxyanion that is formed is called carbonate. Notice that it ends in ate, A-T-E. Carbon, because we're talking about carbon. Carbonate. So the 8 means an oxyanion of carbon. Now, the important thing for you to keep up with is the number of oxygens and the total charge on that oxyanion species. So carbonate, 3 oxygens, total charge is -2. Okay, now keep up with these. Nitrogen. The oxyanion of nitrogen is nitrate. 3 oxygens, total charge -1. Phosphate. 4 oxygens, total charge -3. Sulfate. 4 oxygens, total charge -2. And chlorate. 3 oxygens, total charge -1. Now I know when you see these the first time, you may wonder, how am I going to keep up with this? Believe me, after a short period of time, these will be easy for you. Just keep working at it. So know the eights and then apply the following rules. I sort of say it's sort of like declining a verb. If you have one less oxygen, the 8 becomes an ite. So look at the nitrogen column. Nitrate has 3 oxygens. If I have only 2 oxygens, it becomes nitrite. The ite ending. One less oxygen than an 8 becomes an ite. Nitrite. Now we catch a break because though we have one less oxygen, the total charge on this oxyanion species remain the same, -1. So that part is easy. We just have to know how many oxygens and relate that to the name. Nitrate and nitrite. Phosphorus. The 8 is phosphate. We have one less oxygen, it becomes phosphite. Okay, phosphate, phosphite. Sulfur. Sulfate, we lose an oxygen, it becomes sulfite. So sulfite is SO3 minus 2. Chlorate. Chlorate was ClO3 minus 1. If we lose an oxygen, it becomes chlorite, ClO2 minus 1. So once you know the 8s, you then work on the ites. If you lose another oxygen, you become a hypoite. Now there's only one column that you have to worry about, and that is for chlorine. It becomes hypochlorite, ClO minus 1. So it's lost 2 oxygens from its chlorate stage, it becomes ClO minus 1. Now let me point out that I'm showing only chlorine for the halogens, but the same naming system would occur for bromine. We would have bromate, bromite, hypobromite, and iodine. We would have iodate, iodite, and hypoiodite. Really, you don't have oxyanions for fluorine, so don't worry about those. Now, you can lose oxygens and you become an ite or a hypoite. What about gaining an oxygen? That also you have for the halogens. So chlorate, if you add one more oxygen, becomes perchlorate, ClO4 minus 1. Perchlorate. And yes, you can have perbromate and periodate. All right, so that is the basic naming scheme that you have to know. The 8s, know the 8s, how many oxygens, what the total charge is. Know the ites, that's one less oxygen. And then the hypoites, which happens only for the halogens. And the per-8s, which again happens only for the halogens. Notice that in each of these columns, the charge on the species remain the same. Now, as soon as I said that, you may have looked and said, but there's a row where the charge is changing, and I haven't got to those yet. Those are the hydrogen 8s and the hydrogen ites. The hydrogen 8s are where we add an H plus, a hydrogen ion, to the oxyanion. And when we add an H plus, we add one positive charge. So that makes the total charge on the species more positive by 1. Or in other words, if we look at our first example, carbonate, CO3 minus 2, if we add an H plus, it becomes HCO3 minus 1. Hydrogen carbonate. For phosphate, we can add one hydrogen and become hydrogen phosphate, and it now has a charge of minus 2. But notice also that we can add 2 hydrogens to become dihydrogen phosphate. Okay, sulfate, if we add one H plus, becomes hydrogen sulfate. And likewise for the ites, the same thing happens. Phosphite can become hydrogen phosphite or dihydrogen phosphite. Total charge then becoming minus 2 or minus 1. Sulfite, if we add an H plus, can become hydrogen sulfite. Okay. Notice that it's not hydra or hydro, it's hydrogen sulfate, hydrogen sulfite. Now you might notice that I don't have an entry for adding an H plus to nitrate, for example, or an H plus to chlorate. Can you think of why? It's because if I were to add an H plus to the minus 1 oxyanions, it would now become a neutral molecule. And it wouldn't be on my table as an oxyanion anymore. It would become a neutral molecule. Actually, in this case, these cases, they will be acids, and we'll talk to you shortly as to how we name these acids. And in any case where there's not an entry in this table, it's because we don't have those species. We don't we don't have a carbonite. I mean, I've heard it on advertisements, but it's not a substance. Okay. All right. I think we will pause now so that these videos don't get too long, and then we'll continue on with the second video. All right. Thanks.